Hi everyone, this is Madhav. This is a very complicated video about linear algebra that is going to be frustrating and long and just not mathematically easy. So if you haven't taken a linear algebra course, I wouldn't recommend you watch this video. What we're going to talk about is orthonormal, not orthogonal, orthonormal diagonalization and its applications in computing powers of matrices. It's not that this is an especially enlightening topic, however, it does tie together a lot of different theory from many different parts of linear algebra, which is why I'm talking about this. Also, this kind of stuff has a lot of usage in engineering and physics, so that was something I always used to ask my course instructor for linear algebra, how we're going to use it. So I'll leave these links in the description if you wanna know. That being said, as you can see in the outline, we have 5 main steps to solving this question. We have to take this matrix and multiply it by itself 26 times. It seems a little bit much, but shows why this is more efficient than computing this by itself 26 times. Anyways, we're gonna approach this problem by finding eigenvalues, eigenvectors, making sure that the eigenvectors we have, they are ready for orthonormal diagonalization, not just regular diagonalization. Then going ahead with what we usually do in diagonalization and computing the final answer. This is like 17 pages of stuff, so buckle in, I guess. First off, to find the eigenvalues, we need to get the characteristic polynomial set up. So I'm just defining that over here. You can see all I'm doing is just taking away lambda on each of the diagonal entries of A. And then I set the determinant of this new matrix to 0, which is our regular first 2 steps for finding eigenvalues. I use the expansion formula for determinants to now compute the determinant on the left side. So my goal here is to take a 3x3 matrix, which is big and ugly, and break it down into determinants of 2x2 matrices that I can easily compute with a formula. So I chose to expand along column 1 here. So I took the coefficient, and then I have the cofactor, coefficient, and then the cofactor, and this gets us set up to start computing this equation, start computing our determinant. So now we just need to fill in these cofactor values, so let's just compute those. For the cofactor for position 1, 1, I know that the determinant has to end up without a negative sign in front, because the position, it adds up to an even number. And I just knock out row 1 and column 1 to compute the remaining determinant, and I get this. Simplify a little bit, and then move on to the second cofactor. Again, this time 2 plus 1, that's odd, so I know that I need a negative sign in front. And I'm just going to knock out row 2 up here and column 1, and then compute the determinant of the remaining entries. So now that I have the cofactor, well, both of them, I can substitute them into this equation and then finally solve for my eigenvalues. So I substituted the cofactors here and here. Simplify the equation by collecting like terms here and here, and a bunch of these cancel out. So for example, 2 lambda squared minus 2 lambda squared, 16 lambda, and this they collect, minus 32 plus 32. So after getting rid of a bunch of stuff, I have a much simpler equation. I factor that, noting that over here I end up being left with a difference of squares, so I factor that again, and that lets me solve for the eigenvalues given this remaining equation right here. Alright, step 1 done. Now that I've found the eigenvalues, I can get to what I really care about for diagonalization, which is I need the eigenvectors so that I can use them to construct some matrices that I need for diagonalization. So the important part is using these eigenvalues. Now I can go back to the vector I created up here, the matrix, and I can start computing the eigenvectors. So for the first eigenvalue, lambda is equal to 0, I just substituted that in for lambda, simplified the matrix, and now I just solved the system using Gaussian elimination. I'm just working through a bunch of steps, which you should probably check. I did my best to check them, but you can check that the answer you get is this simplified, almost, well, it's a row echelon form. So now that I have the row echelon form, I can convert that into a solution. So I see that there's a free variable in column 3, which is x3, and the other entries, x1 and x2, they're defined in terms of x3. So I just replace those with whatever, equation alongside x3 I can read, and factor out the x3, and this gives us our first eigenvector. Progress. Now we can move on to the second eigenvector. So we're moving on to another eigenvalue, lambda equals 6, and we do the exact same thing. So just substitute 6 in for the lambdas, simplify, and then use Gaussian elimination to go through, well, just 2 steps here before we get to our solution, noting again that x3 is a free variable because there's no pivots. We simplify, factor out, and then we have our second eigenvector. Note that technically I should be calling this, the eigenspace, declaring all that, and then, declaring that this vector is the basis of the eigenspace, and that's why it's an eigenvector. So I'm just skipping some formalities, but whatever. We have our second eigenvector. One last time with lambda equals -6, which was our last eigenvalue. We go through, substitute that into the matrix, simplify, run Gaussian elimination. It's like a drill by now. As I wouldn't say usual, it doesn't have to be this way, but as is the trend so far, we have a free variable in the third column. So we take our solution, define x1 and x2 in terms of x3, factor out the x3, and we have our last eigenvector. So really, it's not that it's too hard, it's just that it's very long to just even set up the problem and get the information we need so that we can start the diagonalization process. Now, when we've done these repetitive steps, this is usually where we stop with regular diagonalization. With orthonormal diagonalization, Now we have to go we have to go 2 steps further. First of all, we have to make sure that all of these eigenvectors that we found, we have to make sure that they're all orthogonal to each other, and we have to make sure that they're all normal so that they have a magnitude of 1. Sometimes I find that people don't understand how we go about making things normal, so I wanted to do maybe a quick demonstration. So I'm going to open up Geogebra here, which is a graphing platform. Okay, so I have Geogebra open here. Let's just talk about the visuals of the Gram-Schmidt procedure that we're using to get orthogonal vectors. So let's say I have 3 vectors, A, B, I'm just coming up with these off the fly, no particular intention, and C, here we are. I'm going to make these different colors so that we can differentiate between them. Alright, so you can see these vectors are clearly not orthogonal. What could we do if we wanted to create an orthogonal bunch of vectors out of these? Well, let's just do it one at a time. One orthogonal vector in a group of orthogonal vectors at a time. So let's say the first orthogonal vector we picked to be A. So I'm going to disable these for now, as we're going to create a new group of vectors. So the first vector I pick, I'll call it V1, and it's just going to be A. Alright, we don't have to worry about anything because it's just one vector. We don't need it to be orthogonal to anything else yet. Let's take our second vector in the set to be, well, we could try making it B, but then that doesn't guarantee that, we have 2 orthogonal vectors. So what could we do instead? Well, how about this? So we know that perhaps B is not orthogonal to V1 because, B and A, they might not be orthogonal. What if we took away all components of B that went in the same direction as V1? Well, if we did that, then it's kind of like, okay, we have V1 going this way. We want to see which part of B also goes that same way. That's kind of like we're checking, is there some projection of B onto V1? And if so, can we get rid of that? Can we get rid of that component? So let's just do that. We're gonna get rid of, I'm gonna have to use the projection formula here. So we're gonna get rid of the projection of B onto V1. Yep, here we are. So now you can see these 2 vectors, they are at right angles to each other. And the reason is I took away the components that they could share. I took away the components of B that could lie along this vector V1. And I did that by taking away the projection of B onto V1. Now we can do kind of the same thing for V3. So we could say V3 is equal to C because that's our third vector. However, we again have that problem of how do we ensure that it's not pointing in the same direction as either of these other 2 vectors? Well, we just have to subtract away the components of V2 or V1 that could be in the same direction as C. So again, we're gonna use the projection tool for that. So we want to check what components of C are in the same direction as V1 and subtract away that component. And we want to do the same thing for V2. So check which components of C point in the same direction as V2 and subtract away those components. And now you see we have orthogonal vectors. They're all 90 degrees to each other. So this is the visual intuition behind the Graham-Schmidt process. This is what we're doing with orthogonal vectors. When we want to orthogonalize a set, that's just fancy words for saying take away all the parts of the vectors that lie in the same direction. So carrying on here, as we make our vectors orthonormal, I'm just going to do the exact same thing I showed you, so without like actually showing you the visuals. So for the first vector, we can just pick a vector. We don't need to worry about making it orthogonal to others. For the second vector, we have to use our projection that I just showed you. In this case, it turns out that when we dot product these two vectors together, we get 0, which means those vectors were already orthogonal, because this example is nice. That's usually not going to happen. So I'm still going through the motions of this is how we do it in general. And then for our third vector, as I showed you, we just make sure that it's orthogonal to both W1 and W2. So again, use our projection formulas. This isn't hard per se, it's just long, tedious computations. We find that this third vector is also orthogonal to all of them, so this is a very special example. Usually this doesn't happen. So in the end, our orthogonal set just stays the same as all of the original eigenvectors. Finally, last step before we diagonalize, we want to make sure that, you see we have our eigenvectors that I plotted out, they were already orthogonal. The last thing that we want to do is make sure the vectors are normal. So to do that, we're just going to divide by their magnitude, because that's going to be like getting them back to a magnitude of 1. The intuition behind that is like, hey, if you had 8, if you had 8, the scalar, and you wanted to get it back to 1, you wanted it to be a normal scalar, then you just divide by how big 8 is. Well, 8 is 8 big, so 8 divided by 8, you get to 1. With vectors, how big it is, it's not just defined by one value, but multiple values. So that's why we have to divide by their magnitude, but it's the same exact idea. We're dividing a scalar by its magnitude to get it to be normal, 8 divided by 8 to 1, and the same idea with this vector, divided by its magnitude to get its magnitude to be 1. So we do that here, and we get this answer. Here we are. Same thing with W2, get this instead of the original. And last with W3. So this was the original, and here's what it is after normalization. So now you see we have orthogonal vectors, except they're smaller compared to what they were before. So all of this was just set up so that we could finally get to the big thing, the diagonalization and the computation. So to create the diagonal matrix, we're going to have some matrix P, whose columns are just, the vectors that we just created, W1, W2, W3, 1, 2, 3. And then we're going to invert this matrix to get P inverse. To do that, we just had to solve a homogeneous system of equations with multiple augmented columns, and if that was just like way too much math words to go through your head, we just need this thing, this thing, the way that I always remember, okay, that's how we solve for the homogeneous system of equations, is that I think like, okay, we have p, we have to multiply it by something to get in, so that the something we're solving for is p inverse. So I'm like, okay, p times something is going to get us to in, and that always helps me set up the system correctly. Anyways, there's so many fractions here that I tried several times to do this by hand. I failed. So yeah, we had a calculator and it told us that P inverse was this matrix. And now we created an equation, a second one, where you have P inverse AP is equal to D. I know many people who have taken linear algebra courses, they just memorize this formula, but I absolutely adore this series by 3 Blue 1 Brown that actually explains why this is happening. And if you can understand this, good on you. What you need to understand is every matrix is a transformation, and if you understand that, then this will make sense and this formula will be actually intuitive. So I'll link to that 3 Blue 1 Brown series and the exact video where he explains this part, if you want to actually understand, you know, why are we using this formula that we are. So now that we don't really understand why this formula is the way it is, some of you might understand if you understand that matrices represent transformations, but you know, to those of you that understand, we're going to proceed, and to those of you who don't, you can memorize, though I wouldn't encourage it because it's not too hard to understand. Check out the link in the description. Anyways, now that we understand this formula, we're gonna go forward with substituting in P inverse A and P inverse AP, run that computation, and we get D, the diagonal matrix, is this thing. And so we're done part 1 of the problem, I guess. 15 pages later, we have orthonormally diagonalized A, and now we just have to calculate a to the power of 26. Now I'm not saying this computation is easy, it's just much easier than trying to do it with 26 matrices being multiplied one after the other. So if we do our computation now, we're gonna derive the computation formula that will give us a to the power of 26, because, you know, I don't like memorizing. And you'll see we still have like complex operations, but they're complex operations on scalars instead of matrices, so that's much better. So let's take our equation 2. I'm just going to left multiply both sides by the matrix P. You can see P inverse and P, they cancel out. Well, they multiply to get the identity matrix, which we can neglect, so that's why they cancel out. And then we're left with this equation. We're going to right multiply it by the P inverse matrix. You can see what I'm doing is trying to isolate for A. So if we right multiply by the P inverse matrix on both sides, these things quote unquote cancel out, and then we have A left by itself on the left side. And now, because I have that, I can raise it to the power of 26, raise this to the power of 26 as well, so that I can create a formula to work with. But now you might be asking, like, what? We went from a matrix that was raised to the power of 26 to 3 matrices being multiplied together raised to the power of 26. How does that help me? Well, luckily for us, things cancel out. So if we expand this a little bit, so we have these repeated PDP inverse terms, 26 of these in particular, I didn't write all 26. We can see that we can rebracket things, in particular these P inverse P terms, which will cancel out, quote unquote cancel out. And that leaves us with, okay, get rid of this, get rid of this, get rid of this. You can see that what's in the middle is just a bunch of D's. in fact 26 of them being multiplied together. So we can rewrite a raised to the power of 26 with this diagonal matrix raised to a power, and then we have these p and p inverse terms left over at the end that didn't cancel out with anything. D to the 26, this is much easier. You can try it on paper for d squared or d to the third. You'll see that what you have is just the diagonal elements. They are raised to that power that the entire matrix is being raised to. So I substituted in values here, so p d raised to the 26, and then p inverse, and here's the mathematical version of what I just said. Raising a diagonal matrix to the power lets us use the shortcut of just raising the individual scalars to the power, which is much more efficient than entire matrix multiplications. Now, even though scalar exponentiation is more efficient than matrix exponentiation, you still can't do it in your head, because I have no clue what 6 raised to the power of 26 is. I suppose you could simplify the exponents, and you could use this process of if I square 6 and then halve the exponents and whatever, but still it's not fun, because the number you have to keep in track of in the end is this thing, and I don't even know how to say this number, so I wouldn't recommend that you do this in your head. Anyways, put it into a calculator, because we sped up the computation all we could. Now it's calculator's turn. So calculator spits out 6 to the 26, and also 6 to the 26, because the negative doesn't matter with an even exponent. We get this. Right, multiply, so these two matrices, multiply them, and you get whatever this mess is, and then multiply this mess with the left matrix, and here is our final answer for a raised to the power of 26. Yay, I guess. Anyways, yeah, this is our long orthonormal diagonalization process. Just raising things to powers, it's not the only application, so I swear this is useful. Check out the links, I'll put them in the description, and you can say, hey, today I figured out how do I make this happen, whatever this is.